So we're now going to take a look at these things called differentials. And before we do this, if you have not already done so, please make sure you go read that short article called The Calculus Controversy. That was in your packet of in-class things to deal with. A little bit about the history of calculus, and you will have a question or two about this on your upcoming quiz on Unit 5. If you haven't already done so, right now, go take a look at that article. The whole point is calculus was simultaneously developed by two different people working completely independently. They both came up with the same ideas and reached the same conclusions. Now, because they were working independently and really had no idea the other person was doing any work, even though they reached the same conclusions and came up with the same ideas, they used different notation. Newton used notation like this. Y with a dot over it for a derivative, y with 2 dots over it, y with 3 dots over it. This notation became our y prime, our y double prime, our y triple prime. And we've mostly used his notation when dealing with things in this class so far. Leibniz used some different notation. Oops, that's not how we spell it. And that's also not how we spell it. Leibniz used these things called differentials. Little things that look like dx, or dy, or dz, or whatever. While Newton was focusing on finding the rate of change, the slope, all that stuff, Leibniz focused on the change in x, the change in y, the change in z, kind of like a delta x, delta y, delta z, those things. But the advantage to Leibniz's notation is all the variables are treated the same. And here's what I mean by this. The derivative in differential form of x is just dx. If we're using Leibniz's notation, we would say the derivative of x isn't 1, but it's 1 dx, or just dx. In Leibniz's notation again, the derivative in differential form of y is dy. It treats all the variables equally. I'm not going to write this one down, but what's the derivative of z in Leibniz's notation? I hope you just said, and put in Edpuzzle, dz. So, let me show you how to use this. And this is particularly important because the second half of the year, which starts with our unit on integration that's coming up, will focus primarily on Leibniz's notation for calculus rather than Newton's. We use Newton's notation when we talk about derivatives frequently, but we use Leibniz's notation when we deal with integrals. First example. We are going to calculate dy for the function y equals x cubed. I want to calculate dy for y equals x cubed. The first thing I'm going to do is I'm going to find my derivative of y. Well, using Leibniz's notation, my derivative of y is just going to be dy. The derivative of x cubed, well, I know my normal derivative of x cubed is 3x squared, so I'm going to write that down. But then, kind of like using chain rule, I need to multiply this answer by the derivative of the thing that I'm cubing, the derivative of x. And the derivative of x is dx. My derivative in differential form, using Leibniz's notation, is dy equals 3x squared dx. Let me show you two more examples. All we really need to know, though, the derivative of y, dy, derivative of x, dx. Let's say y equals the sine of x squared. The derivative of y. What's the derivative of y? I hope you just said dy. On the right, I need to use three-part chain rule. On the outside, I need to do the derivative of sine. Well, the derivative of sine is, I hope you just said cosine, so I'm going to say cosine x squared. Inside my sine, I had a something squared. What's the derivative of something squared? Well, 2 times that thing, 2 times x. Times, the thing inside that square was an x. What's the derivative of x? Well, what is the derivative of x? We're using Leibniz's notation, so the derivative of x is dx. I can consolidate and say dy equals 2x cosine x squared dx. And that's my derivative in Leibniz's notation. We're going to take a look at one more. Let us deal with this. Y equals x minus 4 squared times 2x plus 3 cubed. Get that copied down. On the left, derivative of y is, I hope you just said dy. On the right, I need to use product rule, and within the product rule, I need to use the chain rule. First, times derivative of the second, x minus 4 squared. Times derivative of the second, I'm going to deal with that cube first. I'm going to say 3 times 2x plus 3 squared times the derivative of the inside. The derivative of 2x plus 3 is 2 times dx. 2 dx. See if you can go do second times derivative of the first. Second, 2x plus 3 cubed times derivative of the first is 2 times x minus 4 to the first times derivative of that inside, derivative of x minus 4, dx. Let's see, this gives me, if I clean it up a little bit, 6 times x minus 4 squared times 2x plus 3 squared dx. We usually stick the dx at the end of each term. Plus 2 times x minus 4 times 2x plus 3 cubed dx. But I want to simplify this. I need to go factor out the GCF. What is the GCF here? Well, let's see. 6, 2, I can take out a 2. X minus 4 squared, x minus 4, I can take out an x minus 4. 2x plus 3 squared, 2x plus 3 cubed, I can take out a 2x plus 3 squared. But they also both have a dx in common, so I'm going to take that out as well. What am I left with? Well, I'm left with a 3 and an x minus 4. And I'm left with a 1. That's nothing. That's nothing. I'm left with a 2x plus 3. Take a moment, just distribute combined like terms over there. Tell me what thing you get inside the parentheses. Let's see, 3x minus 12 plus 2x plus 3, that's 5x minus 9. 2 times x minus 4 times 2x plus 3 squared dx times 5x minus 9. Final thing, though, we really should just stick the dx at the very end. That's what you're going to get used to seeing when we get into our antiderivatives, our integrals. So I'm going to say 2 times x minus 4 times 2x plus 3 squared times 5x minus 9 dx. So just like derivatives, except the derivative of any variable is just d, whatever that variable is.